300 years ago, scientists believed they knew what the world was made of. Tiny, indestructible balls of matter, atoms, solid little objects that click together like the smallest possible bricks, and from those bricks, everything else was assembled. It was a clean picture. It was also wrong. Here is what physics actually claims today, and it is far harder to accept. There are no solid objects anywhere in the universe, not in your body, not in the rock you can throw, not in the core of the sun. When you push your hand against a table and feel resistance, nothing solid is touching anything solid. What you are feeling is one set of fields refusing to overlap with another. The solidity is real as a sensation, but the substance behind it is not what you think. So what is left if matter is removed from the bottom of reality? The answer that modern physics gives is a single word that sounds almost too simple. Fields. Continuous, invisible, filling all of space, present in the emptiest vacuum you can imagine, and every particle that has ever been detected, every electron, every photon, every fragment of light or matter is nothing more than a ripple moving through one of these fields. This is quantum field theory. It is the most accurately tested idea humanity has ever produced, matching experiment to a precision finer than measuring the distance across a continent to the width of a single hair. And it leads to a conclusion that reframes everything. The universe is not a collection of objects sitting in space. The universe may be the space itself, vibrating. To see how we got here, we have to begin in the one place that appears to hold nothing at all. The place to begin is the vacuum, because the vacuum is where our ordinary intuitions break down first and most completely. Picture the emptiest region you can imagine. Take a sealed box and remove all the air from it, every molecule of nitrogen and oxygen, every stray atom drifting through. Then go further, remove the light, cool the walls of the box until they stop glowing with their own heat, because anything warm radiates, and radiation is something rather than nothing. Now you have a box that contains, by every classical definition, absolutely nothing. No matter, no light, no heat. Empty space in its purest form. For most of human history, this is exactly what people assumed empty space was. A stage with no actors on it, a container waiting to be filled, the space between things and nothing more. That picture survived for thousands of years, and it survived because it matches what our senses tell us. When you look at the gap between two objects, you see nothing there. When you wave your hand through air and then through a vacuum, the vacuum offers even less resistance. Emptiness seems like the natural default, the thing that remains when everything else has been taken away. The ancient Greeks argued about whether such a void could even exist, with some insisting that nature abhors a vacuum and that true nothingness was impossible, while others maintained that without empty space, there would be no room for atoms to move at all. But across all those debates, the assumption underneath was shared. Empty space, if it existed, was inert. It did nothing. It had no properties of its own. It was the absence of everything. Quantum field theory says this is one of the deepest mistakes in the history of thought. The vacuum is not empty. It is not inert. It is not the absence of everything. It is, in fact, a churning, restless, energetic medium that fills every cubic centimeter of the cosmos, and the apparent emptiness you perceive is only the surface of something with enormous hidden structure underneath. When physicists calculate what the vacuum actually contains, they do not find nothing. They find activity, constant, unavoidable activity woven into the fabric of space itself. To understand why, we have to confront a principle that sits at the heart of quantum physics, one discovered in the early part of the 20th century and never once contradicted by experiment since. It is called the uncertainty principle, and it places a strict limit on how precisely certain pairs of quantities can be known at the same time. The most familiar version involves position and motion. The more precisely you pin down where something is, the less precisely its momentum can be defined, and the reverse holds as well. But there is another version of this principle, and this is the one that transforms our understanding of empty space. It connects energy and time. Over very short intervals, the energy of a system is not fixed, It cannot be fixed. It fluctuates, and the shorter the interval, the larger those fluctuations are permitted to be. Think about what that means for a region of supposedly empty space. If energy cannot hold perfectly still even in the vacuum, then the vacuum cannot truly be at zero. There must always be some residual jitter, some minimum level of activity that can never be removed, no matter how thoroughly you clean the box. You can take out every particle, every photon, every trace of heat, and still this fundamental restlessness remains because it is not made of anything you can pump out. It is a property of space itself, demanded by the laws of quantum mechanics. Physicists call this the zero-point energy, the energy that persists when everything that can be taken away has been taken away. And the activity is not abstract. In the language of quantum field theory, the vacuum is filled with fields, one for each type of fundamental particle, and these fields are never perfectly still. They quiver. They fluctuate around their lowest energy state, and those fluctuations have real, measurable consequences. Out of this background of trembling fields, brief disturbances rise and fall. Particles appear, exist for a fleeting instant, and vanish again, borrowing energy from the uncertainty in the vacuum and paying it back before the universe can register the debt. These are sometimes called virtual particles, and we will return to them in detail later because they are central to how forces work. For now, the essential point is simpler and more startling. The vacuum is alive with motion. The emptiest space contains a continuous flicker of creation and annihilation, an unending fizz of activity that no amount of cleaning can silence. It is worth pausing on how strange this is and how completely it overturns the older view. In the classical picture, you could imagine reaching a state of absolute rest, a perfect stillness, the true bottom of reality where nothing happens. Quantum field theory says that state does not exist and cannot exist. There is no perfect stillness available anywhere in the universe. The floor is not flat, it vibrates, and this is not a flaw in our instruments or a limit on our ability to measure. It is a feature of the world itself, as fundamental as the speed of light or the charge of an electron. You might reasonably ask whether any of this can be tested, or whether it is simply a peculiar conclusion that falls out of the mathematics with no way to check it against reality. This is the right question to ask, and it is the question that separates speculation from science. A theory that predicts a churning vacuum but offers no way to observe. The churning is not yet physics. It is a story. What makes the quantum vacuum part of science rather than philosophy is that its activity produces effects we can measure in a laboratory, effects that would be impossible if space were truly empty. There is a phenomenon, which we will examine closely in a later part of this story, in which two metal plates placed extremely close together in a vacuum are pushed toward each other by the pressure of vacuum fluctuations, as though the empty space between them were exerting a force. That force has been measured. It matches the prediction. The vacuum, it turns out, can be weighed against itself, and it does not weigh nothing. There is also a deeper and more troubling consequence, one that physicists openly admit they do not fully understand. If the vacuum carries energy, and quantum field theory says it carries a great deal of energy, then that energy should have an effect on the universe as a whole. Energy gravitates, it bends space and influences how the cosmos expands. So we can calculate how much energy the vacuum should contain, and then we can look out at the universe and measure how much vacuum energy actually appears to be present, inferred from the way the expansion of space is accelerating. When we compare these two numbers, the prediction and the observation, they do not match. They do not miss by a little. They differ by an amount so vast that it is widely regarded as the largest discrepancy between theory and experiment anywhere in physics. The calculation says the vacuum should be staggeringly energetic. The sky says the vacuum energy is real but tiny. Somewhere between the equation and the universe, something enormous is being misunderstood. This is the kind of tension that drives science forward, and it tells us something important about where we stand. We have a theory of the vacuum that works beautifully for the small-scale effects we can measure in a lab, predicting the behavior of particles to extraordinary precision. And we have the same theory failing dramatically when we ask it to account for the vacuum on the scale of the whole cosmos. Both of these things are true at once. The framework is among the most successful ever devised, and it also contains at its foundation a problem no one has solved. The emptiness we thought we understood turns out to be the deepest mystery in the room. So the vacuum is our first lesson, and it sets the pattern for everything that follows. What looks like nothing is full. What looks like absence is structure. What looks like the simplest possible thing, the empty space between objects, turns out to be a medium with energy, with activity, with measurable force, and with a contradiction at its heart that points toward physics we have not yet discovered. The stage, it turns out, is not empty, and it was never just a stage. It is part of the play. But to understand what fills this restless vacuum, and to understand why particles are ripples rather than objects, we have to step back and ask a question even older than the vacuum itself. It is the question that every culture and every era has asked in its own way, the question that sits underneath all of physics. What is everything actually made of when you go all the way down to the bottom? That question, simple as it sounds, has a structure to it that becomes clear the moment you start taking things apart. Pick up any object and ask what it is made of. A wooden table is made of fibers. The fibers are made of cells. The cells are made of molecules. And here the chain begins to feel like it is heading somewhere, because the molecules are made of atoms, and for a long time, the word atom marked the end of the road. The word itself comes from an ancient Greek term meaning uncuttable, the thing that cannot be divided any further. The idea was that if you keep cutting matter into smaller and smaller pieces, you must eventually reach a piece that cannot be cut, a final indivisible grain, and that these grains, arranged in different patterns, make up everything. It was a brilliant guess, proposed thousands of years before anyone could test it, and in broad outline, it was correct. Matter does come in discrete pieces. There's a smallest unit of each chemical element. The guess survived because it kept matching reality. But the name turned out to be wrong, because the atom is not uncuttable at all. By the start of the 20th century, experiments had cracked the atom open and revealed that it has parts. There is a dense central core, the nucleus, carrying positive charge and nearly all the mass, and around it, a cloud of much lighter electrons carrying negative charge. So the supposedly indivisible grain was itself a composite object, a tiny system with internal structure. The road did not end at the atom. It kept going. And every time physicists thought they had reached the bottom, they found another level beneath it. The nucleus, that dense central core, was the next thing to come apart. It is not a single lump, but a cluster of smaller particles, protons, and neutrons, packed tightly together. Count the protons and you know which element you are holding, because that count is what makes hydrogen hydrogen and gold gold. For a while, protons and neutrons looked like they might be the true fundamental pieces, the real uncuttable grains that the ancients had been reaching for. But they were not the bottom either. In the second half of the 20th century, experiments that smashed particles together at enormous speeds revealed that protons and neutrons also have internal structure. Each one is made of three smaller objects called quarks, bound together so tightly that they can never be pulled apart and isolated on their own. So the chain extended once more. Table, fiber, cell, molecule, atom, nucleus, proton, quark. And at the quark, for now, the cutting stops. Not because we are certain it is the bottom, but because we have found no evidence of anything smaller inside. Now, here is where the story takes the turn that this entire account is built around. As physicists pushed down through these layers, they were carrying an assumption with them, an assumption so natural that for a long time, no one thought to question it. The assumption was that at the very bottom, whatever you find will be a tiny object, a particle, a small, localized something with a definite position, a little speck of matter sitting at a point in space. The whole image of cutting matter into smaller pieces depends on this. You imagine each piece as a miniature version of the objects we know, just smaller. A grain of sand is like a tiny rock. An atom, we assumed, would be like a tiny grain of sand. A quark would be like a tiny atom, smaller and smaller, but always the same kind of thing. A thing. An object with edges, occupying its own little region, distinct from the emptiness around it. This assumption is where our intuition fails, and it fails in a way that took the greatest minds of the 20th century decades to fully accept. The fundamental constituents of nature are not tiny objects. They do not have definite positions in the way a grain of sand does. They do not have sharp edges. When you examine an electron closely enough, you do not find a miniature ball. You find something that behaves, in some experiments, like a spread-out wave, smeared across a region of space, and in other experiments, like a concentrated point. It refuses to be only one or the other. And this is not a peculiarity of the electron. Every fundamental particle behaves this way. The closer you look at the supposed building blocks of reality, the less they resemble building blocks, and the more they resemble disturbances, patterns, excitations in something underneath. To feel the weight of this, consider how differently a wave and an object behave. An object is here or it is there. You can point to it. It has a location, and if you want it somewhere else, you have to move the whole thing. A wave is not like that. A wave is a pattern of movement in a medium. When a wave travels across the surface of a pond, nothing solid travels with it. The water itself stays roughly where it is, rising and falling in place, while the pattern, the disturbance, moves across the surface. The wave has no fixed location in the way a pebble does. It is spread out. It can pass through another wave and emerge unchanged. It can add to another wave to make a bigger one, or cancel another wave to make stillness. These are not the behaviors of objects. They are the behaviors of patterns in a medium. And these are exactly the behaviors that fundamental particles display when examined with care. So a strange possibility begins to take shape, and it is the possibility that organizes everything that follows. What if the fundamental things are not particles at all, in the sense of tiny objects? What if particles are like the wave on the pond, patterns of disturbance in some underlying medium that fills all of space? Then the electron would not be a thing sitting at a point. It would be a ripple in a medium, a localized vibration, here in the sense that the disturbance is concentrated in this region, but fundamentally a feature of something larger, the way a wave is a feature of the whole pond rather than an object floating on it. In the medium itself, the thing that ripples would be more fundamental than any particle. The particle would be the effect, the medium would be the cause. This is precisely the picture that quantum field theory provides, and the medium it proposes is the field, not one field, but a set of them, one for each type of fundamental particle. There is an electron field that fills all of space, and what we call an electron is a ripple in that field. There is a field for each kind of quark, and the quarks inside protons are ripples in those fields. There is a field whose ripples we call photons, the particles of light. Wherever you go in the universe, even into the deepest vacuum, all of these fields are present, because the fields are not located anywhere in particular. They are everywhere, the way the surface of the pond is present across the entire pond. A particle is simply a place where one of these fields has been excited, where energy has been deposited and a disturbance is moving through. If this is right, it dissolves the old puzzle of what the smallest object is, because there is no smallest object. The chain of cutting, table to fiber to atom to quark, was never going to end in a tiny ball, because tiny balls are not what reality is made of at the bottom. The chain ends in fields, and fields are not the kind of thing you cut. You do not slice a field into pieces, you disturb it, and the disturbances are the particles. Ask how small an electron is, and the question itself starts to dissolve, because you are asking for the size of a ripple, and a ripple does not have a size in the way a pebble does. It has an extent, a shape, a way of being concentrated or spread out, but it is not a little object with a measurable diameter. This also explains something that classical physics could never make sense of, which is why all electrons are identical. Every electron in the universe has exactly the same mass, exactly the same charge, exactly the same properties, to a precision far beyond anything that could happen by chance. If electrons were tiny manufactured objects, this perfect sameness would be a mystery. Manufactured objects always differ a little. But if every electron is a ripple in one and the same field, the field that fills all space, then their sameness is automatic. They are identical for the same reason that all waves on a given pond obey the same rules. They are excitations of the same underlying thing. There is, in a sense, only one electron in the deepest meaning of the word, one field, and the countless electrons we observe are all ripples in it. The idea is elegant, and it is strange, and the natural reaction on first hearing it is to suspect that it is just a metaphor, a convenient way of speaking that physicists adopted because the mathematics was getting difficult. But it is not a metaphor. The field is not a picture laid over the real physics to make it easier to imagine. In quantum field theory, the field is the real physics. The equations are written in terms of fields, the calculations are performed on fields, and the predictions that come out, the ones tested to extraordinary precision in particle accelerators, are predictions about how fields behave. The particle language is the convenient shorthand, the field language is the foundation. Still, an idea this large does not arrive fully formed, and it did not. The notion that invisible fields filling empty space could be the true substance of reality had to be invented, resisted, refined, and proven across more than a century of work. It began not with quantum physics at all, but with a much older puzzle about how objects can push and pull on each other across empty space without touching. And it began in the hands of a man who could barely do mathematics, who drew his picture of the universe in lines rather than equations, and who was dismissed for years before the world caught up to what he had seen. That man was Michael Faraday, and his story matters here not only because of what he discovered, but because of how differently he thought from everyone around him. Faraday came from poverty. He had almost no formal education, no training in advanced mathematics, none of the equipment of a gentleman scientist of his era. He began as an apprentice to a bookbinder, and what saved him was that he read the books he was binding. He educated himself out of them, attended public lectures, took obsessive notes, and eventually talked his way into a position assisting one of the leading chemists of the day. He spent his life in the laboratory, working with his hands, building apparatus, running experiment after experiment. And because he could not express his ideas in equations, he was forced to think in pictures, in physical images of what might be happening. This limitation, which should have held him back, turned out to be the source of his greatest insight, because the picture he formed was closer to the truth than the mathematics of his contemporaries. The puzzle he was working on was an old and genuinely confusing one. A magnet can move a piece of iron without touching it. Bring the magnet close, and the iron leaps toward it across a gap of empty air. Two magnets can push each other apart while held an inch apart with nothing visible between them doing the pushing. The same is true of electric charges. Rub a rod and it will attract scraps of paper from a distance, pulling them up through the air without contact. How does this happen? How does one object reach across empty space and exert a force on another object that it is not touching? This was not a small question. It struck at the heart of how the physical world is supposed to work, because everywhere else in ordinary experience, to push something, you have to touch it. To move the iron, something has to make contact with it. Yet here was a force crossing a gap with nothing in between. The accepted answer in Faraday's time was to not really answer it at all. The prevailing view, inherited from the towering success of Newton's theory of gravity, was that objects simply act on each other across distances, instantly and directly through empty space. This was called action at a distance. Two masses attract each other, two charges attract or repel each other, and the force just reaches across the gap. There was no mechanism, no explanation of how the influence got from one object to the other. It simply did, and the mathematics described how strong the force was at any given separation, and that was considered enough. The numbers worked, the predictions matched. Most physicists were satisfied to calculate the force and not worry about how the empty space in between was involved, because as far as the equations were concerned, the empty space did nothing. The force leapt across it as if it were not there. Faraday could not accept this. To him, the idea that one object could reach across truly empty space and touch another with nothing happening in the gap made no physical sense. There had to be something in the space between, something carrying the influence from one object to the other. And because he thought in pictures, he formed a specific image of what that something might be. He imagined that a magnet does not act directly on distant iron, but instead fills the space around itself with a kind of invisible influence, an arrangement of lines stretching outward in all directions, and that the iron responds to these lines where it sits, not to the distant magnet. He called them lines of force. You can make them visible in a rough way with a simple experiment that school children still perform. Scatter iron filings on a sheet of paper and hold a magnet beneath it. The filings do not lie randomly. They arrange themselves into curved arcs, sweeping from one end of the magnet around to the other, tracing out a pattern in the space around the magnet. Faraday looked at those curves and saw something real. Not a trick of the filings, but a map of an actual condition of the space itself. This was the radical step. Faraday proposed that the space around a magnet is genuinely different from empty space far away from any magnet. It is in a state, a condition, that he pictured as filled with these lines of force. The lines were not just a way of drawing the force for convenience. They were, in his mind, physically present in the space, a real structure occupying the gap between objects. The magnet creates this structure in the surrounding space. The structure extends outward and fills the region, and any iron or any other magnet placed in that region feels a force because it is sitting inside the structure. The force is not transmitted across empty space by magic. It is transmitted by the condition of the space itself, the lines of force, which Faraday increasingly came to think of as a field permeating the region around the source. The word field, in this physical sense, is part of what he gave to physics. It is hard now, with a century and a half of hindsight, to appreciate how strange and unwelcome this idea was at the time. The mathematicians had a perfectly good theory of action at a distance. It calculated forces correctly. And here was a man with no mathematics, proposing that invisible lines fill all of space and carry forces from object to object, based on the pattern of iron filings and his own physical intuition. To many of his contemporaries, this seemed like a step backward, a return to vague qualitative pictures in place of the clean precision of the equations. Faraday could describe his lines of force in words and drawings, but he could not write them down as a rigorous mathematical theory, and in physics, an idea that cannot be made precise is always vulnerable to dismissal. For years, his concept of the field was regarded by many as a useful crutch for someone who could not handle the real mathematics, rather than a description of how nature actually works. But Faraday had something the action at a distance theory did not, which was a series of experimental discoveries that his field picture made sense of, and that the older view struggled to explain. The most important came when he turned the relationship between electricity and magnetism around. It was already known that an electric current produces a magnetic effect, that a wire-carrying current behaves like a magnet. Faraday asked the reverse question: if electricity can produce magnetism, can magnetism produce electricity? He found that it can, but only under a specific condition. A magnet sitting still next to a wire does nothing, but a magnet moving relative to the wire, a changing magnetic situation, drives an electric current through the wire. This is the principle of electromagnetic induction, and it is the basis of nearly every electric generator in the world. Every time electricity is produced in a power plant, whether the energy comes from falling water, burning coal, or splitting atoms, the final step is almost always the same. Something spins a magnet near coils of wire, and the changing magnetic field drives a current. The lights in your home are powered by Faraday's discovery. For our story, what matters is how naturally this fits the field picture and how awkwardly it fits action at a distance. In Faraday's image, the moving magnet changes the field in the space around it, and that changing field, present in the space where the wire sits, pushes on the charges in the wire and drives the current. The field is the active thing. It fills the space, it changes over time, and its changes have physical consequences for anything sitting within it. The space between the magnet and the wire is not an empty gap across which influence mysteriously leaps. It is filled with a field that is doing real work. The more Faraday experimented, the more it seemed to him that the fields were the primary reality and the objects The magnets and wires and charges were just the places where fields were created and detected. He began to suspect that the field might be more fundamental than the matter that produced it, a thought far ahead of his time. There is a particular moment that captures how far his thinking ran. Faraday speculated that the lines of force might have a real existence independent of the magnet, that they were not merely a property of the source, but something that could exist in space on their own. He wondered whether a disturbance in the field could travel, whether you could pluck the lines of force like a string and send a ripple outward through space. He did not have the mathematics to develop this into a theory, and he expressed it cautiously, aware that he was reaching beyond what he could prove. But the intuition was extraordinary. He was groping toward the idea that fields can carry waves, that a disturbance in the electric and magnetic condition of space might propagate from place to place as a traveling ripple. He sensed, without being able to demonstrate it, that this might have something to do with light. The picture was almost complete in his mind, but it was a picture without equations, and a picture alone, however accurate, is not yet physics. What Faraday's fields needed was someone who could take the physical image and translate it into rigorous mathematics, someone who could write down precisely how the fields behave, how they are created, how they change, and how they carry their influence through space. Faraday had given physics a new way of seeing, the space between objects filled with active, structured fields rather than empty and inert. But seeing is not the same as proving, and the lines of force remained, in the eyes of much of the scientific establishment, a vivid but unproven picture. The man who would change that, who would take Faraday's intuition and forge it into one of the most beautiful and consequential theories in all of science, was a generation younger, trained in exactly the mathematics that Faraday lacked. And when he applied that mathematics to Faraday's fields, he would discover something that neither of them had quite dared to claim outright. He would discover what light is. His name was James Clerk Maxwell, and in temperament and training, he was almost the opposite of Faraday. Where Faraday was self-taught and worked in pictures, Maxwell was among the most gifted mathematicians of his generation, fluent in the abstract machinery that Faraday had never learned. He could have dismissed Faraday's lines of force the way many of his peers did, as the vague imaginings of a brilliant experimenter who could not handle equations. Instead, Maxwell did something far more interesting. He took Faraday's physical picture seriously, treated it as possibly true, and set himself the task of finding the mathematics that would make it precise. He read Faraday's work closely and recognized that beneath the absence of equations, there was a coherent and possibly correct vision of how the world worked. His goal became to give that vision a rigorous mathematical form, to write down the laws that the fields obey. This collaboration across a generation, one man supplying the physical insight and the other the mathematical structure, produced one of the great achievements in the history of science. Maxwell gathered together everything that was known about electricity and magnetism, the various separate laws that different experimenters had discovered, and he expressed them all in the language of fields. There was a law describing how electric charges create electric fields. There was a law describing how magnetic fields behave, with their curious property of having no isolated poles, no separate north without a south. There was Faraday's own discovery, the law that a changing magnetic field creates an electric field. And there was a law originally describing how electric currents create magnetic fields that Maxwell would examine more closely than anyone before him. 4 laws describing how electric and magnetic fields are produced and how they relate to each other. Maxwell wrote them all down in the unified language of fields filling space. But as he assembled these laws, Maxwell noticed something wrong. The set was not quite consistent. There was an asymmetry, a gap in the logic. Faraday had shown that a changing magnetic field produces an electric field. Symmetry and consistency suggested that the reverse should also hold, that a changing electric field should produce a magnetic field. But the existing laws, as inherited from earlier experimenters, did not include this. The law describing how magnetic fields are produced only mentioned electric currents, the flow of charges through wires as the source of magnetism. It said nothing about changing electric fields creating magnetism. Maxwell found that without adding this missing piece, the equations contradicted themselves in certain situations. They could not consistently describe what happens, for example, in the gap of a circuit where charge builds up, but no current actually flows across the gap. So Maxwell added the missing term. He proposed that a changing electric field is, in fact, a source of magnetic field, just as a changing magnetic field is a source of electric field. This addition is one of the most consequential single steps in the history of physics, and at first it looked like a small technical fix to make the equations consistent. It was far more than that. Once Maxwell added this term, the equations became symmetric in a profound way. A changing magnetic field creates an electric field. A changing electric field creates a magnetic field. And the moment you have that symmetry, a remarkable possibility opens up, one that Maxwell was the first to see clearly. Imagine you create a disturbance in the electric field somewhere, a sudden change. According to the equations, that changing electric field generates a magnetic field. But that magnetic field is also changing, growing where there was none before, and a changing magnetic field generates an electric field, which is also changing, and so generates a magnetic field, and on and on. The two fields feed each other. The changing electric field produces a changing magnetic field, which produces a changing electric field in an endless self-sustaining cycle. And this cycle does not stay in one place, it moves. The disturbance propagates outward through space, electric and magnetic fields continuously regenerating each other as they go. A self-sustaining ripple traveling through the fields that fill all of space. Maxwell had found exactly what Faraday had only dared to imagine. The fields can carry waves. A disturbance in the electromagnetic field can travel from place to place as a self-propagating ripple, electric and magnetic components weaving together, neither one able to exist alone in the wave, each one constantly creating the other. This was a genuine prediction emerging from the mathematics, not a guess. The equations demanded that such waves should exist, and then Maxwell did the calculation that turned a beautiful piece of mathematics into one of the most important discoveries ever made. He worked out how fast these waves would travel. The speed came out of the equations as a specific number, determined by two quantities that could be measured in the laboratory, quantities describing how strongly electric and magnetic fields respond in empty space. These were not mysterious constants. Experimenters had measured them in ordinary experiments with charges and currents, with no thought of waves or light. Maxwell took these measured values, combined them as the equations instructed, and calculated the speed at which an electromagnetic wave would propagate. The number he obtained was the speed of light. Consider what this meant. The speed of light had been measured independently, through astronomical observations and clever experiments with rotating mirrors, long before anyone connected it to electricity and magnetism. It was a known quantity, sitting in the books, with no apparent relationship to magnets and wires. And now, Maxwell, working purely from the laws of electric and magnetic fields, predicting waves that no one had ever knowingly observed, calculated the speed of those waves and found it matched the speed of light exactly. There was only one reasonable conclusion, and Maxwell drew it. Light is an electromagnetic wave. Light is a ripple in the electromagnetic field, the very field that Faraday had pictured filling the space around magnets and charges. The light from the sun, the light from a candle, the light by which you are reading, all of it is a disturbance traveling through the electromagnetic field, electric and magnetic components regenerating each other as they cross the void. This was a unification of breathtaking scope. Before Maxwell, electricity, magnetism, and light were three separate subjects. Electricity was about charges and currents and sparks. Magnetism was about lodestones and compass needles. Light was about optics, lenses, colors, the behavior of rays. Three different fields of study with no obvious deep connection. Maxwell's equations revealed that they are three aspects of one thing. Electricity and magnetism are not separate forces, but two faces of a single electromagnetic field. And light is simply what that field does when it ripples. One set of equations, expressed entirely in the language of fields, accounted for all of it. The lines of force that Faraday had drawn and that the establishment had dismissed turned out to be the substance of light itself. And the prediction reached further than visible light. The equations did not single out any particular wavelength. They described waves of any size traveling at the same speed, governed by the same laws. Visible light occupied only a narrow band of possibilities. There should be electromagnetic waves with longer wavelengths and shorter wavelengths, invisible to the eye, but otherwise the same kind of thing, ripples in the same field. This prediction was confirmed within decades. Radio waves, discovered and generated deliberately in the laboratory, turned out to be electromagnetic waves with wavelengths far longer than visible light. The same field that carries sunlight carries every radio broadcast, every signal to and from every phone. All of it ripples in the electromagnetic field at different wavelengths. Later came the recognition that other known phenomena fit the same pattern, that the entire range from the longest radio waves through visible light to the shortest, most energetic radiation are all electromagnetic waves, differing only in wavelength, all of them disturbances in Faraday's field. A single field, filling all of space, supporting ripples across an enormous range of scales, and we perceive a sliver of those ripples as the visible world. For the argument this account is building, Maxwell's achievement is a turning point. Faraday had proposed that fields are real, physically present in the space between objects, doing the work of transmitting forces. Maxwell proved it by showing that these fields obey precise mathematical laws, and that those laws predict correctly the existence and speed of light. The field was no longer a crutch or a picture. It was a rigorously described physical entity whose behavior could be calculated and confirmed to high precision. The space around us is genuinely filled with the electromagnetic field, and that field is not a passive backdrop. It carries energy, it supports waves, it brings us the light of distant stars across the emptiness of space. By the end of the 19th century, the field had earned its place as a fundamental feature of reality, at least for electricity, magnetism, and light. And yet Maxwell's triumph, complete as it seemed, contained the seeds of its own undoing. His theory described light as a continuous wave, a smooth disturbance that could carry any amount of energy, divisible without limit, like ripples on water that can be made as gentle or as fierce as you like with no smallest possible step. This continuous picture worked beautifully for a vast range of phenomena. But as the new century opened, experimenters began to probe how light interacts with matter at the smallest scales, how it is emitted and absorbed by individual atoms. And there, the smooth, continuous wave began to fail. The energy of light, it turned out, did not come in any amount you pleased. It came in discrete pieces, indivisible lumps, as though the continuous wave were secretly made of grains. The smooth world that Maxwell had so beautifully described was about to crack. The crack appeared first in a problem that seemed almost too mundane to overturn physics. Physicists were trying to understand the light given off by hot objects. Everything, when heated, glows. A poker pulled from a fire glows red. Heat it more, and the color shifts toward orange, then yellow, then a brilliant white, and if you could heat it further still, toward blue. This is universal. The color of the glow depends only on the temperature, not on what the object is made of, and that universality was a clue that something fundamental was at work. Physicists wanted to predict from the laws they had exactly how much light of each color a hot object should emit at a given temperature. They had Maxwell's theory of electromagnetic waves, and they had the established laws of heat and energy, and they put them together to calculate the answer. The calculation gave a result that was not just slightly wrong, it was catastrophically, absurdly wrong, in a way that exposed something broken at the foundation. According to the classical calculation, a hot object should radiate an infinite amount of energy. The reasoning went like this. The light coming off a hot object could have any wavelength, and the classical theory said that each possible wavelength should carry on average the same share of energy. But there is no limit to how short a wavelength can be. You can always have a shorter one, so if every wavelength gets an equal share of energy, and there are infinitely many possible short wavelengths, then the total energy radiated must be infinite, with most of it pouring out at the shortest wavelengths in the ultraviolet and beyond. This prediction was obviously false. A warm object does not blast out infinite energy. It does not even glow particularly brightly at short wavelengths. A piece of metal at room temperature emits almost no visible light at all, let alone a lethal flood of ultraviolet. The theory predicted a disaster that plainly does not happen. The mismatch was so stark that it earned a name capturing its absurdity, the ultraviolet catastrophe, and it signaled that the smooth classical picture of light contained a deep error. The resolution came in the year 1900 from a German physicist named Max Planck, and it came reluctantly. Planck was a conservative thinker, deeply rooted in classical physics, and he did not set out to start a revolution. He was simply trying to find a formula that matched the observed glow of hot objects, the actual measured curve of how much light of each color comes off at each temperature. He found that he could reproduce the correct curve, the one that experiments showed, but only if he made an assumption that he himself found troubling and at first regarded as a mere mathematical trick. The assumption was this: the energy of light is not continuous. It cannot be emitted in any amount. It comes only in discrete packets, in divisible units, and the size of each packet depends on the wavelength of the light. Light cannot carry half a packet or a third of a packet. It carries one packet or two or three, but never anything in between. This single assumption fixed everything. To see why, return to the ultraviolet catastrophe. The disaster came from the idea that every wavelength gets an equal share of energy, including the infinitely many short wavelengths. But Planck's packets changed the situation completely, because the size of the packet grows as the wavelength gets shorter. At short wavelengths, the smallest possible packet of energy is large, and here is the key. To emit even a single packet at a short wavelength, the object needs to gather a large amount of energy in one place at one time, and at any given temperature. That is statistically unlikely. The object usually does not have enough energy concentrated to make even one of those large, short wavelength packets, so it emits almost nothing at those wavelengths. The flood of short wavelength radiation, which the classical theory predicted, simply cannot occur, because the energy to make those packets is rarely available. The packets choke off the catastrophe. With this assumption, Planck's formula matched the measured glow of hot objects perfectly, across all temperatures and all colors. Planck had introduced the quantum, the discrete packet of energy, and with it, the constant of nature that sets the size of these packets, a fundamental number that now appears throughout physics and is named after him. But Planck himself was uneasy. He treated the packets as a calculational device, a strange necessity to get the right answer, and he hoped that some deeper explanation would eventually show that energy was really continuous after all and that the packets were an artifact. He did not believe at first that light truly comes in lumps. He thought the lumpiness was somehow about how matter emits and absorbs light, not about light itself. The idea that light is genuinely, fundamentally discrete was a step he was not prepared to take. It would take someone bolder to insist that the packets were real. That someone was Albert Einstein, and the year was 1905. Einstein took Planck's reluctant packets and declared that they were not a trick at all, but a description of how light actually is. Light, Einstein proposed, is genuinely made of discrete units of energy. When light travels, when it is emitted and absorbed, it behaves as though it comes in indivisible grains. He applied this idea to a puzzle that had resisted explanation, the photoelectric effect, in which light shining on a metal surface knocks electrons out of it. The details of this effect were baffling under the wave theory of light. According to Maxwell's smooth waves, brighter light, carrying more energy, should knock electrons out with more energy, and the color of the light should not matter much. But that is not what happens. The energy of the ejected electrons does not depend on how bright the light is. It depends on the color, on the wavelength. Dim light of the right color ejects electrons with a certain energy, and making the light brighter ejects more electrons, but does not give any of them more energy. Below a certain color threshold, no electrons come out at all, no matter how intensely you shine the light. Einstein's packets explained all of this immediately. If light comes in discrete units, and the energy of each unit depends on the color, Then, knocking out an electron is a matter of a single packet striking a single electron and giving up its energy. A brighter light has more packets, so it knocks out more electrons, but each packet still carries the same energy as before, so each ejected electron comes out with the same energy. Change the color, and you change the energy of each packet, which changes the energy of the ejected electrons. And if the color is too far toward the long wavelength end, each packet carries too little energy to free an electron at all, so no amount of brightness helps, because brightness only adds more underpowered packets. The threshold, the dependence on color rather than brightness, the whole pattern that made no sense for a continuous wave, fell into place the moment light was treated as discrete. These packets of light would later be named photons, and they are the particles of light, the lumps in which the electromagnetic field delivers its energy. Here, then, was a genuine crisis at the heart of physics, and it is worth stating it plainly because it is the tension out of which quantum field theory eventually grew. Maxwell had proven, with overwhelming success, that light is a wave, a continuous ripple in the electromagnetic field. The evidence for the wave nature of light was enormous. Light bends around obstacles, spreads through openings, and produces interference patterns, alternating bands of brightness and darkness where waves add and cancel, exactly as waves should. There was no doubting that light is a wave. And yet Planck and Einstein had now shown with equally compelling evidence that light is made of discrete packets, that it delivers its energy in indivisible lumps, that it behaves like a stream of particles. There was no doubting that either. Both pictures had powerful experimental support, and the two pictures seemed to contradict each other directly. A wave is spread out and continuous and divisible without limit. A particle is localized and discrete and indivisible. Light, somehow, was both. This was not a comfortable situation, and physicists did not embrace it gladly. For more than a decade, the wave-particle duality of light, as it came to be called, sat as an unresolved paradox, a sign that something basic was not understood. But the strangeness did not stay confined to light. The next step, taken in the 1920s, was to ask whether the same duality might apply to matter. If light, which everyone had thought was a wave, turns out to also behave as particles, might electrons, which everyone had thought were particles, also behave as waves? This question, when it was tested, gave an answer that broke the old picture of reality apart completely and opened the door to fields. Because the answer was yes. The proposal that matter might behave as waves came from a French physicist, Louis de Broglie, and at the time it must have seemed almost reckless. Light, which had always been considered a wave, had been shown to behave as particles. De Broglie suggested the symmetric possibility. Electrons, which had always been considered particles, tiny charged specks orbiting the nucleus of an atom, might behave as waves. He even wrote down how long the wave associated with a moving particle should be, a wavelength determined by the particle's momentum with the same fundamental constant that Planck had introduced, setting the scale. It was a bold guess, supported at first by little more than a sense of symmetry and a few suggestive pieces of reasoning. If nature was going to blur the line between waves and particles for light, perhaps it did so for everything. The test came within a few years, and the result was decisive. The defining behavior of a wave is interference, the way two waves combine to reinforce each other in some places and cancel each other in others, producing a pattern of alternating intensity that particles simply cannot make. If electrons are waves, then a beam of electrons should produce an interference pattern under the right conditions. Experimenters fired electrons at a crystal whose regularly spaced atoms act like a fine grating and looked at where the electrons landed. They did not land in a simple way. They landed in a pattern of alternating bands, concentrated in some directions and absent in others, exactly the interference pattern that waves produce and that particles should be incapable of producing. Electrons, the supposed tiny specks of matter, were behaving as waves. De Broglie's guess was correct. Matter, like light, has a wave nature. The experiment that captures the full strangeness of this most clearly is the one performed by sending particles, one at a time, through a barrier with two narrow openings, two slits, and recording where each one lands on a screen behind. Consider first how waves behave in this setup. A wave reaching the two openings passes through both at once, emerging as two new waves that spread out and overlap. Where the crests of the two overlapping waves coincide, they add and produce brightness. Where a crest meets a trough, they cancel and produce darkness. The result on the screen is a pattern of alternating bright and dark bands, the unmistakable signature of interference, the proof that something passed through both openings at once and combined with itself. Now send electrons through the same apparatus, one electron at a time, with long gaps between them, so that each electron is alone in the device and cannot interact with any other. Each electron, when it arrives at the screen, makes a single small mark at a single spot, exactly as a particle should. It does not arrive spread out. It arrives at one place, a localized point, the way a thrown pebble strikes a wall at one location. This looks like particle behavior, clear and unambiguous. But let the experiment run, sending thousands of electrons through one after another, each making its own single mark, and watch what the accumulated pattern of marks becomes. The individual points, building up one by one, gradually form the bands of an interference pattern. The spots cluster where the bright bands would be and avoid where the dark bands would be. Each electron arrived as a localized particle, yet collectively they trace out the pattern that only waves can make. This is the heart of the mystery, and it is worth dwelling on because it cannot be reconciled with the old picture by any clever trick. Each electron went through the apparatus alone. There was no other electron for it to interfere with, and yet the pattern that builds up is an interference pattern, which requires that something pass through both openings and combined with itself. The conclusion that the physics forces upon us is that each single electron, in some sense, passed through both openings at once, traveled as a spread-out wave exploring both paths, interfered with itself, and only became localized to a single point at the moment it struck the screen and was detected. Between emission and detection, the electron was not a tiny ball following one path. It was a wave spread across the apparatus, present at both openings simultaneously. Only when measured did it appear as a particle at a definite location. If you try to catch it in the act, the strangeness deepens. Place a detector at the openings to see which one each electron actually goes through, to catch it choosing a path. When you do this, when you force the electron to reveal which opening it passed, the interference pattern vanishes. The electrons begin to behave like ordinary particles, each going through one opening or the other, and the bands disappear, leaving only the simple result you would expect from specks of matter passing through two holes. The act of detecting which path the electron takes destroys the wave behavior. Watch for the particle and you get a particle. Do not watch, and the electron travels as a wave through both paths at once. The electron is neither simply a wave nor simply a particle. It is something that can display either face depending on how it is questioned, and that has no complete description in the everyday language of objects. For a while, this was described as wave-particle duality, the idea that quantum objects are sometimes waves and sometimes particles, switching between the two natures. But duality, framed that way, is not really an explanation. It is a restatement of the puzzle. To say that an electron is sometimes a wave and sometimes a particle does not tell us what it is when no one is looking, or why measurement should change its nature, or how a single object can pass through two openings at once. The language of waves and particles, both borrowed from the world of ordinary objects, was straining to describe something that is neither. What was needed was a different conception altogether, one in which the wave behavior and the particle behavior were not two contradictory natures awkwardly stuck together, but two aspects of a single underlying thing. And the single underlying thing, it would turn out, is the field. Here is how the field resolves the tension, and it is the central move of this entire account. Do not think of the electron as a tiny ball that sometimes acts like a wave. Think instead of an electron field, filling all of space, exactly like the electromagnetic field that Faraday and Maxwell described, but for electrons. This field can carry waves, disturbances that spread out and travel and interfere, just as the electromagnetic field carries light waves. When an electron moves through the two-slit apparatus, what is really moving is a wave in the electron field, a disturbance that genuinely spreads out genuinely passes through both openings, and genuinely interferes with itself. That is why the interference pattern appears. The wave nature is the field nature. The field is doing what fields do, supporting a spreading, interfering wave. But the field has a further property, the quantum property, which is where the particle nature comes from. The energy in the electron field cannot be deposited or extracted in any amount. Like Planck's packets of light, the electron field delivers its energy only in discrete, indivisible units. When the spread-out wave in the electron field reaches the screen and gives up its energy, it cannot give up a little here and a little there, smeared across the whole screen. It must give up one whole unit of the field's energy at one place. That is why each electron arrives as a single localized mark. The particle nature is the discreteness of the field's energy. The electron is not a ball, and it is not a wave. It is a packet of energy in the electron field, a ripple that spreads like a wave but is exchanged in discrete lumps like a particle. The two natures that seem to contradict each other are simply the wave behavior and the discrete energy of one underlying field. This is the resolution that quantum field theory provides, and it is worth appreciating how it dissolves the paradox rather than merely restating it. The question was, how can the electron be both a spread-out wave and a localized particle? The answer is that it is neither. It is an excitation of a field. The field genuinely spreads out and interferes, which gives the wave behavior, and the field genuinely delivers its energy in discrete packets, which gives the particle behavior. There is no contradiction because there is only one thing, the field, and waves and particles are just two of the things that a quantized field does. The electron in the double slit passes through both openings because the field wave passes through both. It lands at one point because the field's energy is exchanged in one lump. Both facts are true at once because both are properties of the same field. And this picture applies to everything, not just electrons. Every kind of fundamental particle has its own field, filling all of space, and every particle is a packet of energy in its field. The photon is a packet in the electromagnetic field. The electron is a packet in the electron field. Each type of quark has its field. The fields are the fundamental layer of reality, and particles are what we observe when those fields are excited and exchange their energy in discrete units. The everyday picture of reality as tiny objects moving through empty space is replaced by a picture of fields filling all space, with the objects being ripples in the fields. This is not a metaphor laid over the physics. It is the physics. But to build this picture into a complete and consistent theory, physicists had to overcome an obstacle that the simple field idea on its own could not handle. They had to make the quantum behavior of fields agree with the other great revolution of the early 20th century, the one that reshaped space and time themselves. That other revolution was Einstein's theory of relativity, and at first, it seemed to belong to an entirely different domain from the quantum world. Quantum mechanics, as it had been developed through the 1920s, was a theory of the very small, of atoms and electrons and the discrete packets of energy that govern them. Relativity was a theory of the very fast and the very large, of how space and time behave when objects move at speeds approaching the speed of light, and of how gravity shapes the geometry of the cosmos. Two separate revolutions, each overturning classical physics in its own way, each spectacularly successful in its own domain. The trouble was that the two theories, when examined closely, did not fit together. And reality does not come divided into separate domains. The same electron that obeys quantum mechanics also moves through space and time, and if it moves fast enough, it must obey relativity too. A complete theory would have to honor both. Making them agree turned out to be extraordinarily difficult, and the effort to do it is what gave birth to quantum field theory in its mature form. To see why the two theories clashed, we have to understand what relativity demands. The special theory of relativity, which Einstein published in the same remarkable year as his work on light packets, rests on a single startling principle. The speed of light is the same for everyone, no matter how they are moving. This sounds harmless until you follow its consequences. In ordinary experience, speeds add up. If you walk forward on a moving train, Your speed relative to the ground is the train's speed plus your walking speed. But light does not work this way. Shine a beam of light from a moving train, and its speed relative to the ground is not the train's speed plus the speed of light. It is just the speed of light, the same as if the train were standing still. For this to be true, something has to give. And what gives is our notion of absolute space and time. Measurements of length and duration must depend on motion. A moving clock runs slow. A moving object contracts along its direction of motion. Two events that one observer sees as simultaneous, another observer, moving differently, sees as happening at different times. Space and time are not the fixed universal backdrop that everyone had assumed. They are flexible, woven together into a single four-dimensional fabric, and how that fabric divides into space and time depends on how you move through it. One consequence of relativity matters more than any other for the story of fields, and it is the most famous equation in all of science, the relation that energy and mass are equivalent, that mass is a form of energy and energy a form of mass, related by the speed of light. The practical meaning of this equivalence is that energy can be converted into mass and mass into energy. Given enough energy concentrated in a small enough region, that energy can become matter, can produce particles that were not there before. And matter can convert back into energy, particles vanishing and leaving energy behind. This is not a rare or exotic process. It happens constantly. It is how the sun shines, converting mass into the energy of sunlight. It is what happens in particle accelerators, where the energy of high-speed collisions materializes into showers of new particles. Mass and energy are interchangeable, and particles can be created and destroyed whenever enough energy is available in the right form. Now consider why this is fatal to the early quantum theory of a single particle. The quantum mechanics of the 1920s was built to describe a fixed number of particles. It wrote down equations for one electron, or a handful of electrons, and tracked how their waves evolved over time. The number of particles was assumed to stay constant. The electron you started with was the electron you ended with. But relativity says this assumption is false. With enough energy, particles can be created and destroyed. An electron can be born where there was none. A particle and its counterpart can annihilate and vanish. The number of particles is not fixed. It changes. And a theory built to describe a fixed number of particles simply cannot handle a world where particles wink in and out of existence. The early quantum mechanics had no way to describe the creation of a new particle or the destruction of an existing one. It was a theory of permanence in a world that relativity revealed to be impermanent at its core. The two frameworks were not just awkward together, they were fundamentally incompatible, because one assumed a fixed cast of characters and the other insisted that the cast can grow and shrink. This is where the field becomes not just an appealing picture, but a necessity. Think again about what a field is. A field is a quantity that has a value at every point in space, and that value can change over time. The electromagnetic field can be strong here and weak there, can rise and fall, can support waves that come into being and fade away. Crucially, a field can hold any number of excitations. You can have no waves in it, a calm, flat field. You can have one wave, two waves, 100 waves. You can create a new wave by depositing energy, and you can destroy a wave by removing energy. The number of ripples in a field is not fixed. It is exactly the kind of thing that can grow and shrink. And this is precisely what relativity demands and what the old particle-counting quantum mechanics could not provide. If particles are ripples in fields, then creating a particle is just adding a ripple to a field, and destroying a particle is just removing one. The variable number of particles that relativity requires becomes natural, because fields naturally support a variable number of excitations. So the marriage of quantum mechanics and relativity forces the field picture upon us. You cannot have a consistent theory of the quantum world that respects relativity, and still imagine that the fundamental things are a fixed number of tiny particles. The moment you take seriously that energy can become matter and matter can become energy, you need something that can hold a changing number of particles, and that something is the quantized field. The field is permanent and fundamental. It is always there, filling space in the vacuum and everywhere else. But the particles, the ripples in the field, are transient. They are created and destroyed as energy flows into and out of the field. The field is the actor that persists. The particles are the field's fleeting expressions. This is the conceptual core of quantum field theory, the framework that finally made quantum mechanics and relativity work together, and it took the better part of 2 decades to construct in full. The construction was not smooth, and it was driven as much by specific puzzles as by grand principles. One of the most important puzzles concerned the electron itself. Physicists wanted an equation that would describe the electron correctly, honoring both quantum mechanics and relativity at once. The equation that quantum mechanics had used for the electron was not built to be consistent with relativity. It treated space and time differently, in a way that relativity forbids, since relativity insists that space and time be woven together and treated on the same footing. So the challenge was to find a new equation for the electron, one that respected the deep symmetry between space and time that relativity demands, and that still described the quantum behavior of the electron, its wave nature, and its discrete energy. This was a precise mathematical problem, and it would be solved by a young, intensely reserved English physicist whose approach to physics was guided by an almost mystical faith in mathematical beauty. When he found his equation, it would do far more than describe the electron. It would, in solving one problem, predict the existence of an entire category of matter that no one had ever seen, a mirror version of every particle, opposite in charge but identical in mass. It would predict antimatter, and the prediction would emerge not from any experiment, not from any observation of the strange new matter, but purely from the demand that the mathematics be consistent. The equation would have solutions that no one asked for and no one initially wanted, solutions describing particles with properties that seemed impossible. And rather than discard them, the physicist would take them seriously and follow them to their conclusion. It is one of the most remarkable episodes in the history of science, a case where pure mathematics, pursued for its own consistency, revealed a hidden half of the universe before anyone had laid eyes on it. The physicist was Paul Dirac, and he was unlike almost anyone else in the field. He spoke rarely and only with precision, distrusted loose talk, and approached physics with a conviction that the laws of nature must be mathematically beautiful, that beauty and truth were somehow the same thing in the deepest equations. Where others reasoned from experiments toward theory, Dirac often reasoned from mathematical elegance toward predictions, trusting that if an equation was beautiful enough and consistent enough, nature would turn out to obey it. This faith guided him to one of the most consequential discoveries of the 20th century, and the way he arrived at it shows how far pure mathematical reasoning can reach into the physical world. The problem Dirac set himself was the one just described. He wanted an equation for the electron that would be consistent with both quantum mechanics and special relativity. The existing quantum equation for the electron failed the test of relativity because of how it treated space and time. Relativity demands that space and time enter the equations on an equal footing, woven together, neither one privileged over the other. The existing equation did not do this. It handled time in one way and space in another, which is exactly what relativity forbids. Dirac wanted to repair this, to find an equation that described the electron's quantum behavior while treating space and time with the symmetry that relativity requires. He approached the problem with great mathematical care, insisting that the equation take a particular clean form, and after considerable effort, he found it. The equation he wrote down, which now bears his name, described the electron beautifully. It was consistent with relativity. It correctly accounted for properties of the electron that earlier equations had to put in by hand, including a subtle magnetic property of the electron that fell straight out of Dirac's mathematics as if it had been waiting there all along. By any measure, it was a triumph. But the equation came with a complication that Dirac could not ignore, and his refusal to ignore it is what made him great. The equation had more solutions than he had bargained for. Alongside the solutions describing ordinary electrons with positive energy, the mathematics produced an equal set of solutions describing states of negative energy. These negative energy solutions were deeply troubling. In physics, systems tend to settle toward the lowest available energy, the way a ball rolls downhill to the lowest point it can reach. If states of negative energy existed, and if they extended downward without limit, then every electron in the universe should tumble down into them, cascading toward ever lower energy, radiating away energy as it fell, never finding a bottom to rest on. The stable matter of the world would be impossible. Atoms would collapse. The existence of negative energy solutions seemed to predict a catastrophe that plainly does not happen, since matter is manifestly stable. Many physicists faced with such solutions would have concluded that the equation was flawed, or would have simply discarded the unwanted solutions as unphysical artifacts to be ignored. Dirac did not discard them. He took the position that if the mathematics produced these solutions, and if the equation was otherwise correct and beautiful, then the solutions must mean something. The task was to find an interpretation that made physical sense, that explained why the catastrophe does not occur while still honoring the mathematics. His first attempt at an interpretation was ingenious and strange. He proposed that the negative energy states are not empty, but already entirely full. Imagine that throughout all of space, every available negative energy state is already occupied by an electron, an infinite sea of negative energy electrons filling the vacuum. Because of a quantum rule that forbids two electrons from occupying the same state, the ordinary positive energy electrons cannot fall into the negative energy states, since those states are already taken. The catastrophe is averted because there is no room. The vacuum in this picture is not empty at all, but a completely filled sea of hidden electrons, and what we call empty space is this filled sea, which we do not notice precisely because it is uniform and complete. This strange picture, the filled sea, led Dirac to a prediction that would prove far more important than the picture itself. Suppose you take one of the electrons out of the negative energy sea, lifting it up into a positive energy state where it becomes an ordinary visible electron. You have now created an ordinary electron, but you have also left behind a hole, a gap in the otherwise complete sea, a place where a negative energy electron is missing. Dirac asked what this hole would look like, how it would behave, and the answer was remarkable. The absence of a negative energy electron, the hole, would behave like a particle with positive energy, just like an ordinary electron, but with the opposite electric charge. Where the electron is negatively charged, the hole would appear positively charged. The missing negative would present itself as a present positive. So the equation, through this interpretation, predicted the existence of a new particle, identical to the electron in mass but opposite in charge, a positive twin of the electron. At first, Dirac was cautious about what this new particle might be, even wondering whether the hole might somehow be the proton, the known positively charged particle. But the proton is far heavier than the electron, and the hole had to have exactly the electron's mass so that identification could not work. The conclusion that the mathematics forced was that there must exist a previously unknown particle with the same mass as the electron but opposite charge, a genuine antiparticle to the electron. This was an extraordinary thing to claim. No one had ever seen such a particle. There was no experimental hint of its existence. The prediction came entirely from taking the mathematics seriously, from insisting that the equation's solutions must correspond to something real. Dirac was predicting a hidden form of matter purely on the strength of an equation's internal consistency. The vindication came within a few years, and it was complete. An experimenter studying the particles that rain down from space in cosmic rays found tracks that could only be made by a particle with the mass of an electron but a positive charge. It was exactly the particle Dirac's equation had predicted. It was given the name positron, the positive electron, and it was the first piece of antimatter ever observed. Dirac had reasoned his way to the existence of an entire category of matter, unseen and unsuspected, purely from the demand that his equation be consistent with relativity and quantum mechanics. The prediction of antimatter from pure mathematics stands as one of the most striking demonstrations that the deep structure of the physical world can be uncovered by following the logic of the right equations, even into territory that no experiment has yet explored. The discovery of the positron was only the beginning, because antimatter turned out to be entirely general. It is not only the electron that has an antiparticle. Every kind of matter particle has a corresponding antiparticle, identical in mass, opposite in charge, and certain other properties. There is an antiproton, an antineutron, antiparticles for each type of quark. Matter and antimatter come in mirror pairs throughout nature. And when a particle meets its antiparticle, something dramatic happens that connects directly back to relativity. They annihilate. The particle and antiparticle vanish, and their mass is converted entirely into energy, usually in the form of photons, packets of light flying away from the point of annihilation. Conversely, given enough concentrated energy, a particle and antiparticle can be created together, born as a pair out of pure energy. This is the creation and destruction of particles that relativity demanded and that the old quantum mechanics could not describe, now appearing concretely as the annihilation and creation of matter and antimatter. And here, the deeper meaning of Dirac's filled sea begins to give way to something cleaner and more powerful, the full field picture. The image of an infinite sea of hidden electrons filling the vacuum was ingenious, but it was awkward, and it worked only for electrons, not for other kinds of particles. The mature understanding, which quantum field theory provides, dispenses with the sea entirely and replaces it with the field. There's an electron field filling all of space. An ordinary electron is a ripple in that field, a positive energy excitation. An anti-electron, a positron, is also an excitation of that same field, a different kind of disturbance corresponding to the antiparticle. Creating an electron-positron pair is exciting the field in a way that produces both kinds of ripple at once, paid for by the energy supplied. Annihilation is the reverse. Two ripples in the field combining and giving up their energy to the electromagnetic field as photons. There is no need for a filled sea. There is just the field, capable of supporting particles and antiparticles as different excitations, capable of having them created and destroyed as energy flows in and out. Dirac's equation, understood in the language of fields, describes not a single electron but the entire electron field, with all its possible electrons and positrons, all its creation and annihilation, woven into one consistent quantum and relativistic whole. This is the moment the central image of this entire account comes fully into focus. The electron is not a thing. It is a ripple in a field that fills the universe, a field that obeys an equation consistent with relativity, a field that can support both matter and antimatter, that can have its excitations created and destroyed, that is present in every region of space, including the deepest vacuum. Every electron everywhere is a disturbance in this one field, and what is true for the electron is true for every kind of particle. The universe, at its foundation, is a collection of fields, and everything we call matter is the set of ripples moving through them. But these fields are not the smooth, calm fields of classical physics. They are quantum fields, and in the quantum vacuum, they are never still. To understand what that restlessness means, we have to return to the vacuum we began with and look at what is happening in the empty space between the particles. Return, then, to the vacuum, but return to it now equipped with the field picture, because only with fields in hand can we understand what the emptiness is actually doing. We established at the outset that the quantum vacuum is not still, that the uncertainty principle forbids any field from holding perfectly motionless at zero, that there is an irreducible jitter built into the fabric of space. Now we can say more precisely what that jitter consists of. Each field that fills the universe, the electron field, the electromagnetic field, every field for every kind of particle, is constantly fluctuating in the vacuum, trembling around its lowest energy state, never quite reaching the perfect calm that classical physics would allow. And out of these fluctuations, something extraordinary happens. Particles appear and disappear, not permanent particles, not the kind you can capture and study, but fleeting ones, born from the energy uncertainty of the vacuum and vanishing again almost as soon as they form. These are called virtual particles, and they are among the strangest and most consequential features of quantum field theory. To understand where they come from, recall the energy-time form of the uncertainty principle. Over very short intervals, the energy of a system is not precisely defined and can fluctuate, and the shorter the interval, the larger the possible fluctuation. Now, combine this with the relativistic fact that energy can become matter. If the vacuum can have a brief fluctuation in energy, and if energy can turn into particles, then for a very short time, the vacuum can produce particles out of nothing but its own energy uncertainty, provided those particles vanish again quickly enough that the borrowed energy is repaid before the universe can register the loan. A particle and its antiparticle can appear together, drawn from the vacuum's fluctuating energy, exist for a fleeting instant, and then annihilate each other, returning their energy to the vacuum. The whole event happens so fast, and the particles exist for so brief a time that they can never be directly captured. They are virtual, in the sense that they are not the permanent, observable particles of the ordinary world, but transient flickers in the fields, borrowing energy from uncertainty and paying it back almost immediately. The picture this gives of the vacuum is one of ceaseless activity. Everywhere in space, at every instant, particle-antiparticle pairs are flickering into existence and annihilating back into the vacuum, an unending fizz of creation and destruction. The empty space between the stars, the empty space inside an atom, the empty space in this room, all of it is alive with these brief appearances and disappearances. The vacuum is less like an empty stage and more like the surface of a boiling liquid, constantly churning with momentary disturbances, except that the churning never stops and never settles, because it is driven by the fundamental uncertainty woven into quantum physics. This is what physicists mean when they say the vacuum is not empty. It is full of virtual particles, full of fluctuating fields, full of activity that can never be removed because it is a property of the fields themselves. Now, a natural and skeptical reaction is to ask whether this is real physics or merely a colorful way of talking about the mathematics. If virtual particles can never be directly observed, if they vanish before they can be caught, then in what sense do they exist at all? This is the right question. And the answer is what elevates virtual particles from a picturesque story to a cornerstone of physics. Virtual particles, though never directly observed, produce effects that can be measured, effects that would not occur if the vacuum were truly empty and the fields truly still. The fizzing background of virtual particles leaves fingerprints on the observable world, and those fingerprints have been measured with staggering precision. The vacuum's activity is not a metaphor. It is a contributor to real quantitative predictions that match experiment to many decimal places. The most precise of these involves the magnetic property of the electron. The electron behaves like a tiny magnet, and the strength of that magnetism can be predicted by theory and measured by experiment. If the electron were a simple isolated particle, its magnetism would have a particular value, calculable from the basic equation. But the electron is never truly isolated, because it is surrounded by the fizzing vacuum, constantly interacting with the virtual particles that flicker around it. The electron is continually emitting and reabsorbing virtual photons, briefly surrounded by virtual electron-positron pairs, embedded in the restless activity of the fields. All of this activity slightly alters the electron's magnetism, shifting it away from the simple value by a small amount. Quantum field theory allows this shift to be calculated, accounting for the contributions of all the virtual processes, and the calculation produces a number. That number can be compared with the measured magnetism of the electron. The agreement between the calculated and measured values is among the most precise in all of science, matching to a level of accuracy that would be like measuring a distance of thousands of kilometers and being correct to within the width of a human hair. This extraordinary agreement is only possible because the calculation includes the effects of the virtual particles. Leave them out, and the prediction is wrong. Put them in, and it matches reality to a precision that is almost difficult to comprehend. The fizzing vacuum is real, and the proof is in the decimal places. Virtual particles also explain something that classical physics could never properly account for, which is how forces actually work. We saw that Faraday struggled with action at a distance, with the question of how one object can push or pull another across empty space. His answer was the field, filling the space between objects and carrying the influence. Quantum field theory refines this answer in a remarkable way. The forces between particles are carried by virtual particles exchanged between them. When two electrons repel each other, they are not reaching across empty space through some mysterious action at a distance. They are exchanging virtual photons, ripples in the electromagnetic field passed back and forth between them, and the exchange of these virtual photons is what produces the force. One electron emits a virtual photon, the other absorbs it. And through this exchange, momentum is transferred and the electrons push apart. The force is a conversation, a continuous exchange of virtual particles between the interacting objects. This is the modern understanding of how forces work, and we will return to it in detail, because it transforms the whole notion of what a force is. For now, it is enough to see that virtual particles are not idle curiosities. They are the carriers of the forces that hold the world together. There is something philosophically arresting about all of this, and it is worth pausing to register it. The vacuum, the emptiest possible space, the thing we naturally think of as nothing, turns out to be the source of the forces that structure reality and the cause of measurable effects on real particles. Nothing in the quantum world is not nothing. It is a seething reservoir of activity, a medium of fluctuating fields and flickering virtual particles. And that activity is woven into everything. The stability of atoms, the magnetism of the electron, the forces between charges, all of it depends on the restless quantum vacuum. Remove the activity, and you would not have a cleaner, simpler universe. You would have no universe at all, because the activity is part of what makes the fields behave as they do. The emptiness is not the absence of physics. It is one of the most physically active things there is. But if the vacuum is full of energy, full of fluctuating fields and virtual particles, a troubling question presses forward, and it is the same question we glimpsed at the very beginning. How much energy does the vacuum contain? If every field in the universe is fluctuating in every region of space, and if there are countless fields and infinitely many points in space, then the total energy of the vacuum, when you try to add it all up, threatens to become enormous, perhaps infinite. This is not a vague worry. It is a concrete problem that emerges when physicists try to calculate the energy of the quantum vacuum, and the answer that comes out is vastly larger than anything observed. The vacuum energy, by the natural calculation, should be so large that it would dominate the universe, bending space so severely that the cosmos as we know it could not exist. Yet the universe is here, expanding gently, with only a tiny trace of vacuum energy detectable in the way that expansion is subtly accelerating. The calculation and the observation disagree by an almost unimaginable margin. This is the same contradiction we met at the outset, now seen from the inside, and it remains one of the deepest unsolved problems in physics. But before we can weigh that problem fully, we need to confront the question of whether the vacuum's energy can be detected at all, whether there is any direct laboratory evidence that empty space carries energy and that virtual particles are truly present. And there is. It comes from an experiment of beautiful simplicity, in which two plates of metal placed close together in a vacuum are pushed toward each other by nothing but the pressure of empty space itself. That experiment grows out of a prediction made in 1948 by the Dutch physicist Hendrik Casimir, and the prediction is so direct that it serves as one of the clearest demonstrations that the vacuum carries energy. Casimir reasoned as follows: the electromagnetic field fills all of space, and in the vacuum it fluctuates, supporting virtual photons of every possible wavelength, an endless spectrum of vacuum disturbances at every size. Now imagine placing two flat metal plates parallel to each other, very close together, in an otherwise empty vacuum. The plates impose a condition on the electromagnetic field between them. Just as a guitar string fixed at both ends can only vibrate at certain wavelengths, the ones that fit neatly between the fixed endpoints, the electromagnetic field between two metal plates, can only support virtual photons whose wavelengths fit properly within the gap. Wavelengths too long to fit between the plates are excluded from the region between them. But outside the plates, in the open vacuum, there is no such restriction, and virtual photons of all wavelengths are present, including the long ones that cannot fit in the gap. This creates an imbalance. Between the plates, the vacuum fluctuations are restricted to certain wavelengths, so there are fewer of them. Outside the plates, the full spectrum of fluctuations is present, so there are more. The vacuum is, in a sense, denser outside the plates than between them, because more kinds of virtual photons are allowed outside than inside. And this difference produces a pressure. The richer vacuum outside pushes inward more strongly than the thinned vacuum between the plates pushes outward, and the net effect is that the two plates are pushed toward each other. Empty space pushes them together. There is nothing between them but vacuum, no air, no field source, no conventional force, and yet they are drawn together by the difference in vacuum fluctuations inside and outside the gap. Casimir calculated the strength of this attraction, predicting exactly how it should depend on the spacing between the plates, with the force growing rapidly as the plates are brought closer. For a long time, this prediction was difficult to test because the force is extremely small and only becomes appreciable when the plates are brought astonishingly close together, separated by distances comparable to a small fraction of the width of a human hair. At such tiny separations, keeping two plates perfectly parallel and measuring the faint force between them is an enormous experimental challenge. But the experiment was eventually performed, and performed with increasing precision over the decades, and the result confirmed Casimir's prediction. The plates are indeed pushed together. The force is real, it has the predicted strength, and it depends on the separation in exactly the way the theory said it should. There is now no serious doubt that the Casimir effect is real, that two uncharged plates in a vacuum experience an attractive force arising purely from the fluctuations of the electromagnetic field in empty space. Think carefully about what this experiment demonstrates, because its significance is easy to understate. Two plates, carrying no charge with nothing between them but vacuum, are pushed together by a measurable force. There is no conventional explanation for this force. The plates are not magnetized, they are not electrically charged, there is no material between them transmitting a push. The only thing between them is empty space, and empty space, in the classical picture, exerts no force at all. The fact that a force exists and that its strength matches the prediction derived from vacuum fluctuations is direct laboratory evidence that the vacuum is not empty, that it contains fluctuating fields with real energy, and that those fields can exert real, measurable forces on physical objects. The Casimir effect is, in a meaningful sense, a way of detecting the energy of empty space, of confirming that the quantum vacuum is the active, fluctuating medium that the theory describes rather than the inert nothingness of classical physics. The Casimir effect also sharpens the puzzle of vacuum energy, the great unsolved problem we have circled several times. The effect demonstrates that vacuum energy is real, that it has physical consequences, that it can push plates together. So we cannot dismiss vacuum energy as a mathematical fiction. It is there, and it does things. But this makes the discrepancy between the calculated and observed amounts of vacuum energy all the more pressing. If the vacuum genuinely carries energy, as the Casimir effect confirms, then that energy should gravitate, should affect the expansion of the universe, should have consequences on the largest cosmic scales. And when physicists calculate how much vacuum energy there should be, by adding up the contributions of all the fluctuating fields, they get a number that is staggeringly, almost incomprehensibly larger than the amount actually observed in the cosmos. The disagreement is often described as the worst quantitative prediction in the history of physics, a mismatch not of a few percent or even a few times, but of a factor so vast that writing it out would require a long string of zeros. To feel the scale of this problem, consider what the calculation suggests and what observation reveals. The naive calculation of vacuum energy, taking the fluctuating field seriously all the way down to the smallest scales, gives an energy density so enormous that through its gravitational effect, it would curl space up on itself almost instantly, making a universe in which galaxies, stars, and observers could never form. Space would be so violently warped by its own vacuum energy that nothing stable could exist. Yet we observe a universe that is large, old, and gently expanding, with a vacuum energy that is not zero, but is fantastically small compared to the prediction. The universe is expanding at an accelerating rate, and the most natural explanation for that acceleration is a small positive vacuum energy, a faint pressure built into space that pushes it to expand ever faster. This observed vacuum energy, which goes by the name dark energy in its cosmological role, is real and has been measured through careful observation of distant exploding stars and the large-scale structure of the cosmos. But it is tiny, vastly smaller than the calculation says it should be. Theory predicts an ocean. Observation finds a single drop. No one knows how to resolve this. It is one of the genuine frontiers of physics, a place where our best theory, quantum field theory, which succeeds so spectacularly in predicting the magnetism of the electron and countless other quantities, fails dramatically when asked to predict the energy of the vacuum on cosmic scales. Various ideas have been proposed. Perhaps there is some symmetry or principle not yet discovered that causes most of the vacuum energy to cancel out, leaving only the tiny remainder we observe. Perhaps the calculation is being done incorrectly in some fundamental way that will become clear only with a deeper theory. Perhaps the value is what it is for reasons connected to the existence of observers, a controversial line of reasoning suggesting that only universes with small vacuum energy can give rise to galaxies and life, so that any universe containing observers must have a small value regardless of why. Each of these ideas has supporters and critics, and none is established. The honest statement is that we have direct evidence the vacuum carries energy, we have a theory that should let us calculate that energy, and the calculation gives an answer wrong by an enormous margin, and we do not yet know why. It is a measure of how much remains to be understood beneath the surface of even our most successful theories. What the Casimir effect establishes beyond dispute, however, is that the field picture is not a mathematical convenience, but a description of something physically real. Empty space exerts forces. Virtual particles leave measurable traces. The fields that fill the universe have energy and consequences, even when no ordinary particles are present. We began this account with the claim that the vacuum is not empty, and we can now see that this claim is supported not only by elegant theory, but by direct experiment, by plates that move when nothing classical should move them. The fields are real, the vacuum is active. And this brings us to a question that the Casimir effect raises in passing, but that deserves its own full examination, because it lies at the heart of how the entire material world holds together. If virtual particles being exchanged can push two plates together, what else do they do? The answer is that the exchange of virtual particles is the very mechanism of force itself, the way every push and pull in nature is actually accomplished. And understanding this transforms our picture of what it even means for two objects to interact. To understand force as exchange, begin by setting aside the everyday image of a force as a kind of invisible rope or rigid rod connecting two objects, pulling them together or holding them apart. That image is intuitive but wrong at the fundamental level. In quantum field theory, a force between two particles is something more dynamic and more surprising. It is mediated by the exchange of other particles, the force-carrying particles, passed back and forth between the interacting objects. When two particles attract or repel, they are continuously throwing force-carrying particles at each other and catching them. And this ceaseless exchange is what we perceive, on the large scale, as a smooth, continuous force. The force is not a static connection, it is a transaction, a constant traffic of particles between the bodies involved. The clearest example is the electromagnetic force, the force between electric charges, the one Faraday and Maxwell described with their fields. In quantum field theory, this force is carried by photons, the particles of light, the ripples in the electromagnetic field. When two electrons repel each other, they do so by exchanging virtual photons. One electron emits a virtual photon, a brief ripple in the electromagnetic field, and the other electron absorbs it. In emitting the photon, the first electron recoils slightly, and in absorbing it, the second electron is pushed, and the net result of countless such exchanges is that the two electrons move apart. The repulsion we observe is the accumulated effect of this continuous photon traffic. The same mechanism, with different details, produces attraction between opposite charges. The electromagnetic force, in all its manifestations, from the spark of static electricity to the light of the sun to the chemical bonds that hold molecules together, is the exchange of photons between charged particles. This idea, that forces are carried by exchanged particles, is sometimes illustrated with a simple physical analogy, though, like all analogies, it must be handled with care. Imagine two people standing on frictionless ice, throwing a heavy ball back and forth. When one person throws the ball, they recoil backward from the force of the throw. When the other catches it, they are pushed backward by its impact. So with each exchange, the two people drift apart. The throwing and catching of the ball produces an effective repulsion between them, without any rope or rod connecting them, purely through the exchange of the ball. This captures something of how exchanging particles can produce a repulsive force. The analogy struggles to explain attraction, since throwing a ball would seem to always push the throwers apart, and explaining how exchange can also pull objects together requires the deeper quantum mathematics rather than the simple picture. But the analogy does convey the essential and counterintuitive point. A force does not require a physical connection between objects. It can arise purely from the exchange of particles passed between them. Each of the fundamental forces of nature in this framework has its own force-carrying particle, its own type of exchanged ripple, drawn from its own field. The electromagnetic force is carried by the photon. The strong nuclear force, which binds quarks together inside protons and neutrons and holds the atomic nucleus together against the electric repulsion of its protons, is carried by particles called gluons, named for the way they glue quarks together. The weak nuclear force, which is responsible for certain kinds of radioactive decay and plays a crucial role in the nuclear reactions that power the sun, is carried by a set of heavier particles. Each force is the exchange of its characteristic carrier. Each carrier is a ripple in its own field, and the whole structure of forces becomes a structure of fields and the particles exchanged between the things those fields act upon. The forces that shape the world, from the binding of atomic nuclei to the attraction between magnets, are all conversations conducted in the language of exchanged particles. The properties of the force-carrying particles determine the properties of the forces themselves, and this connection is both elegant and deep. Consider the range of a force, how far it reaches. The electromagnetic force has unlimited range. The electric attraction between charges, the magnetic influence of a magnet, the light from distant galaxies. All of these reach across any distance, growing weaker with separation, but never cutting off entirely. This unlimited range is tied directly to a property of the photon. The photon has no mass. A massless force carrier can, in effect, be exchanged across any distance, however large, so the force it mediates reaches everywhere. Contrast this with the weak nuclear force, which has an extremely short range, reaching only across distances far smaller than an atomic nucleus, dying away to nothing almost immediately. This short range is tied to the fact that the carriers of the weak force are very massive particles. A massive force carrier is difficult to exchange across large distances because producing even a virtual one requires a large amount of borrowed energy. And by the uncertainty principle, the larger the borrowed energy, the shorter the time it can be borrowed for, and the smaller the distance it can travel before it must be repaid. So massive carriers give short-range forces, and massless carriers give long-range forces, and the reach of each force in the world is set by the mass of the particle that carries it. The structure of the forces reflects the structure of the fields and their excitations. This way of understanding forces also illuminates why some forces are strong and others weak. Why the strong nuclear force overwhelms the electromagnetic repulsion inside the nucleus, holding protons together despite their mutual electric repulsion, while the weak force is feeble by comparison. The strength of each force is determined by how readily its carrier is emitted and absorbed, by how strongly the relevant field couples to the particles it acts upon. The strong force is strong because its coupling is large, because quarks emit and absorb gluons readily and copiously. The weak force is weak in part because its carriers are so massive that they are difficult to exchange. Each force has its own character, set by the nature of its field and its carrier, and together these forces account for essentially everything that happens in the physical world, from the structure of atoms to the burning of stars to the radioactive decay of unstable nuclei. There is one force, however, that resists this beautiful scheme, and its resistance is one of the great unsolved problems of physics. That force is gravity. Gravity is, in our everyday experience, the most familiar of all forces, the one that holds us to the ground and governs the motion of planets and stars. Yet gravity has stubbornly refused to fit into the framework of quantum field theory that works so well for the other forces. By analogy with the others, gravity should be carried by its own force-carrying particle, a massless ripple in a gravitational field, a particle that has been given the name graviton in anticipation of its discovery. And in many ways, gravity does behave as though it could fit the pattern, since it has unlimited range, consistent with a massless carrier. But when physicists try to build a full quantum field theory of gravity, treating it like the other forces, the mathematics breaks down. The calculations produce nonsensical, infinite answers that cannot be tamed by the methods that work for the other forces. Gravity, described by Einstein as the curvature of space and time rather than as a force in the ordinary sense, has so far refused to be unified with the quantum description of the other three forces. Reconciling gravity with quantum field theory remains one of the deepest and most actively pursued problems in all of physics, the search for a theory of quantum gravity that would complete the picture. But setting gravity aside, the other three forces, the electromagnetic, the strong, and the weak, do fit the framework of fields and exchanged particles, and they fit it with extraordinary precision. Over the middle decades of the 20th century, physicists assembled these three forces and all the known particles of matter into a single comprehensive framework, a catalog of all the fundamental fields and how they interact, a theory that has been tested against experiment more thoroughly than any other in history and has passed every test. This framework brings together the matter particles, the force-carrying particles, and the fields underlying all of them into one structure, the most complete description of the fundamental constituents of reality that we possess. It is called the Standard Model of Particle Physics, and it represents the culmination of the field idea, the point at which the universe is described, as fully as we can currently manage, as a collection of interacting quantum fields. To appreciate what it accomplishes and where it still falls short, we need to look at the full catalog of fields it contains. The Standard Model is, at its core, a complete inventory of the fundamental fields of nature and the rules by which their ripples interact. And the first thing to appreciate about it is how few ingredients it actually requires. For all the apparent complexity of the material world, with its countless substances and structures, the Standard Model builds everything from a remarkably small number of fundamental fields. The matter we encounter, in all its variety, is composed of just a handful of particles, each a ripple in its own field, and these particles fall into a clear and orderly classification that the Standard Model lays out with precision. The matter particles divide into two families. The first family is the quarks, the particles that combine to form protons and neutrons, and hence the nuclei of atoms. There are 6 kinds of quark, distinguished by their masses and certain other properties, and they are conventionally grouped into pairs. The lightest pair, called up and down, are the ones that make up ordinary matter. A proton is made of 2 up quarks and 1 down quark, bound together. A neutron is made of 1 up quark and 2 down quarks. Since protons and neutrons make up the nuclei of all atoms, and since atoms make up all ordinary matter, nearly everything you have ever touched is built, at the deepest level, from up and down quarks rippling in their fields, bound together by the strong force. The other 4 kinds of quark, heavier than the up and down, do not form stable everyday matter. They appear in high-energy processes, in cosmic rays and particle accelerators, and they decay quickly into lighter particles. But they are part of the full catalog, 6 quark fields in all, each filling space, each capable of supporting its characteristic ripple. The second family of matter particles is the leptons, and the most familiar lepton is the electron, the particle whose field we have followed throughout this account. Like the quarks, the leptons come in 6 kinds, grouped into pairs. The electron is the lightest charged lepton, and it is accompanied by 2 heavier charged cousins, particles much like the electron but more massive, which also decay quickly and do not form stable matter. Alongside these 3 charged leptons are 3 electrically neutral leptons called neutrinos, exceedingly light and almost ghostly particles that barely interact with anything at all. Neutrinos stream through the universe in vast numbers, produced in the nuclear reactions of stars and in radioactive decays, and they pass through ordinary matter almost without trace. Countless neutrinos from the sun are passing through your body every second, almost none of them interacting, slipping through the empty fields between the particles of your matter as though you were not there. The neutrinos are leptons too, ripples in their own fields, and they complete the lepton family, 6 in all to match the 6 quarks. So, the matter content of the Standard Model is 12 fundamental particles, 6 quarks and 6 leptons, each a ripple in its own field, and from these 12, all the matter in the universe is built. There is a striking pattern in how they are arranged, which the Standard Model organizes into 3 generations. The first generation contains the lightest particles, the up and down quarks and the electron and its neutrino, and these are the particles that make up ordinary stable matter. The second and third generations contain heavier copies of the same pattern, particles with the same charges and similar behavior, but greater mass, which are unstable and decay into the lighter first-generation particles. Why nature should repeat the pattern 3 times, why there should be 3 generations rather than 1, is not explained by the Standard Model. It is simply observed to be the case. The theory describes the particles, but does not say why there are exactly 3 families of them, a gap that hints at some deeper structure not yet understood. Alongside the 12 matter particles are the force-carrying particles, the ripples in the force fields that mediate the interactions between matter. We have met them in the previous discussion of how forces work. The photon carries the electromagnetic force, a single massless particle, the ripple in the electromagnetic field. The strong force is carried by the gluons, of which there are several varieties, binding quarks together inside protons and neutrons. The weak force is carried by a set of heavy particles, 3 of them, responsible for radioactive decay and certain nuclear reactions. These force carriers, together with the matter particles, make up the active content of the Standard Model. 12 matter particles, a set of force carriers, each one a ripple in a corresponding field, all of them interacting according to precise rules. From this catalog, the theory constructs a description of nearly all known physical processes that do not involve gravity. What makes the Standard Model so impressive is not merely that it catalogs these particles, but that it predicts their behavior with breathtaking accuracy. The theory does not just say which particles exist, it says how they interact, how likely various processes are, what happens when particles collide, how they decay, what new particles can be produced and in what proportions. And these predictions have been tested again and again in particle accelerators that smash particles together at enormous energies and record the debris in exquisite detail. Over and over, the Standard Model has predicted the outcomes correctly, often before the relevant particles or processes were observed. Particles whose existence the theory required were searched for and found, with the predicted masses and properties. The agreement between the Standard Model and experiment, across an enormous range of phenomena, is one of the great achievements of human knowledge, a triumph of the field picture taken to its fullest development. The universe, in the domain the Standard Model covers, genuinely does appear to be made of these interacting quantum fields, and the theory describes them with a precision that leaves little room for doubt that it is capturing something deeply true about reality. And yet the Standard Model, for all its success, was for decades missing a crucial piece, and the gap was not minor. As originally constructed, the elegant mathematics of the theory had a peculiar and troubling feature. The equations worked beautifully, but only if all the particles were massless. The deep symmetry that made the theory consistent and gave it its predictive power seemed to require that the fundamental particles have no mass at all. This was a disaster, because the particles manifestly do have mass. The electron has mass. The quarks have mass. The carriers of the weak force are very massive indeed. If the theory demanded masslessness, but reality showed mass everywhere, then something essential was missing, some mechanism that could give the particles their masses without destroying the beautiful symmetry that the theory needed in order to function. The particles had to acquire mass somehow, in a way that the equations could accommodate, and for a time it was not clear how this could be done. The solution to this problem, proposed in the 1960s and confirmed only decades later, is one of the most remarkable ideas in the entire framework, and it involves yet another field, different in character from all the others. This field would fill all of space like the others, but it would do something none of the others do. It would not be zero in the vacuum. Even in empty space with no particles present, this field would have a non-zero value everywhere, a constant background presence permeating the entire universe. And the particles of the standard model would acquire their masses by interacting with this ever-present field, dragging against it as they move, the interaction manifesting as the resistance to acceleration that we call mass. The field would give mass to the particles without violating the symmetry of the equations, resolving the great difficulty at the heart of the standard model. This is the Higgs field, and its discovery would be one of the crowning confirmations of the entire field picture of reality. The Higgs field, then, stands apart from everything else in the catalog. Every other field we have considered rests when undisturbed at zero. Remove all the ripples from the electron field and it falls silent. Remove all the light from the electromagnetic field and it settles to nothing. Their natural lowest energy state is emptiness, and a particle is a departure from that emptiness, a ripple raised above the calm. The Higgs field breaks this rule. Its lowest energy state, the configuration it prefers to settle into, is not zero. It is some non-zero value present in every region of space, in the deepest vacuum, in the gap between galaxies, inside the atoms of your own body. There is no place you can go to escape it, because its preferred condition is to be switched on everywhere at once, a permanent uniform background filling the universe. And this single peculiar fact, that one field refuses to settle to zero, is what allows the entire standard model to describe a world with mass in it, a world where matter is heavy and slow and able to clump into stars and planets and living things, rather than a world of massless particles streaming forever at the speed of light, unable to build anything at all. So the question that opens the next stage of this story is no longer whether the field picture is correct, but what it costs us to take it seriously all the way down. We have followed reality from the solid table to the atom, from the atom to the quark, from the quark to the field, and from the field to a vacuum that is never still. We have seen forces dissolve into exchanges and particles dissolve into ripples. Now we are asked to accept that even the mass of matter, its very heaviness, the most tangible property anything has, is not built into the particles themselves, but is borrowed from a field that fills all of space. The weight of the world, on this account, comes from the emptiness. To understand how that can be, we have to look closely at the strange field that does not vanish, and ask how an invisible presence filling the cosmos can reach into every particle and give it the property we call mass.